Okay, so continuing with protective circuit protecting devices, part 3, number 3. And we're moving on to miniature circuit breakers, MCBs. Right, so this should be something that we're very familiar with by now. We've all come across an MCB. So, what do we have? An MCB has two types of tripping mechanisms, right? One that opens on a short circuit, one for an overcurrent. Contains a set of silver contacts enclosed within an arc chute. The arc created during opening of the contacts is electromagnetically drawn to the arc chute. This lengthens, cools, and deionizes the arc, extinguishing it safely. The contacts are opened by a spring-loaded trip mechanism actuated by a thermal and electromagnetic current sensor element. Two sensors may work individually or in combination. Cool. What does it mean? Inside of MCB, we know this stuff, right? We have our thermal, which senses overheat, so bimetal, and as we have an overcurrent, it heats up and will slowly move away, which activates the tripping mechanism. Alternatively, when we get that very high short circuit current, that is going to travel through a solenoid, essentially a small solenoid inside there. That solenoid, that's a little electromagnetic piston, right? So that high current flowing through creates a large magnetic field. A small current flowing through there won't do anything. The magnetic field's not big enough. But when we get a large magnetic field through that solenoid, it's going to create a big magnetic field, and it's going to move that piston, and that piston hits the tripping mechanism and it trips off. In addition to that, we have the arc chute, which is like a bunch of little plates close together, and so when it opens, that the arc gets directed through those plates, between the little plates, and so each time it jumps across, it's taking more and more energy to create that arc, so that reduces the energy of each arc, and will extinguish the arc, which, as we saw in the last video, once our arc is extinguished, that is, circuit is now protected. We've shut that circuit down, opening those contacts. Okay. So our two sensors provide a fairly long time delay for small overloads, up to 5 times the rating of the MCB, up to 5 times the rating. Very short time delay for heavy overloads, 10 times the rating. So that's our electromagnetic and thermal. And instantaneous tripping for short circuit currents above 10 times. So up to 5 times, pretty slow, and that's working on the thermal action. Up to 10 times, it's happening pretty fast, and that's the thermal and or the electromagnetic part of the MCB. And then over 10 times, it's going to happen just like that, fast. So that's our short circuit, right? And that's the electromagnetic action. Cool. And here's our diagram. You do need to have a good look at this and try your best to memorize those parts. We have the solenoid here. Let's start at number 1, the bimetal strip. So that's this guy here. So remember, our bimetal strip is just like any other bimetal strip. When it heats up, when current flows through it, it'll heat up. When too much current flows through it, it's going to heat and bend. It's going to bend away, bend downwards, and that's going to activate the tripping mechanism, which is number 2, the tripping lever in here. Tough to really see what that's pointing at. Nevertheless, as it says there, number 2 is the tripping lever. Number 3 is the spring, which is holding, well, that's going to pull the contacts are being held in place, and when the tripping lever moves, no longer holding the contacts in place, then the spring is going to pull that down, or is it pushing it up? Spring is pushing it up, I think, which is going to move the contacts and break our switch open, which is number 4, the contacts there. Number 5 is our solenoid. So now we're talking about the electromagnetic part. So we can see there that coil around there. So the current is flowing through that coil. When it gets really high, we get a magnetic field there. And this part in the center, the little piston there, is going to be pushed down to the armature, which will again activate the tripping lever. And lastly, number 7, we have the splitter plate. So our arc is going to be directed through here. So in order for an arc to be created or maintained, it has to jump across each one of those individual plates there. It obviously becomes increasingly difficult, and therefore it's going to assist the extinguishing of the arc. the extinguishing of the arc, which is what we're trying to do, right? Because there's no point in opening the contacts and then letting that arc continue uncontrolled. Circuit breakers are now used in many switchboards and distribution boards, particularly in domestic switchboards. In addition to its uses as a switch to open the circuit, a circuit breaker has tripping mechanisms that cause it to open on short circuit and overcurrent. MCBs are so named because they are relatively miniature versions of the large circuit breakers used in large installations and power stations. Miniature circuit breakers are sealed so that the calibration cannot be tampered with and are totally enclosed. Right, all of that means exactly what it says. Domestic, yeah, we'll see these mostly in domestic. It's pretty rare now to go into houses, other than, I guess, old ones, and find something other than circuit breakers. Obviously, you would have seen in our classrooms, we have majority of, I think all of our protection in those classrooms is circuit breakers. Most commercial buildings will be circuit breakers in the switchboards. When we start getting to large industrial factories, warehouses, that kind of thing, then we're starting to see the HRCs, right? Because our short circuit currents become higher. But certainly, even in industrial, commercial settings, within offices, for lighting and normal power points and that sort of stuff, that's all still generally controlled by circuit breakers. Really easy to reset, right? So it trips, I can go and reset it, and a little bit easier to use as an isolator. HRC fuse, I need to physically pull that fuse out, which is fine, but then the question is, well, how do I prevent somebody putting something back in there? Not that people should, but we have to assume when we're isolating something that the dummy is going to come along and try and turn it back on. So what do you do with that? That's the question. With an MCB, we don't have that problem. We put a little lock over it, that little locking screw down mechanism, put our lock in, and no one can turn that back on. Great. They're really great for the vast majority of things that uses in terms of protection. Okay, so we've got here information about the two types of tripping mechanisms again, which we have talked about. I won't go into that again. Okay, so here's our thermal action. Let's have a look at this. The thermal type of MCB operates on a principle that the bimetal strip will bend when heated. That's normal. That's the same as what's happening in a thermostat, various other things. We've come across this concept a lot, right? Either the circuit current passes through a heater coil, which in turn heats the bimetal strip. So the current in the coil is heating a little current in the circuit is heating a small coil, which will heat the bimetal strip. Or the current's going straight through the bimetal strip, which will heat the bimetal strip by itself. And here we have a little diagram of how that works. Current flow coming through here, through here, through here, down here, and that will be our output there. And we have our contacts closed. When things start to move, then the latching bar, the plunger rather, pushes the latching bar. The latching bar is holding, see here, they're holding the contacts closed. As soon as that latching bar moves, then the contact is free to open, and therefore circuit is open. Magnetic action. The magnetic force produced by an electromagnet can be used to unlatch the circuit breaker and give an instantaneous trip when the current through the circuit breaker exceeds a predetermined value. We go through here. Again, we've got our same latching mechanism there, same contacts, but now we have a little coil. So now we've got a little piston on the other side of the latching mechanism. That little coil there, when a very high current flows through, as I said before, it's going to move that piston, which will move the latching bar, which stops the will no longer hold the contact. And remember, we've got a spring in here as well, which is actually going to push that push those contacts. So once that latching bar has moved, there's nothing holding the contacts closed. Spring pushes it, and we open the circuit once again. And here we have the combination of the thermal and magnetic action. Combining the features of both actions, a thermal magnetic breaker provides instant action on short circuits, yet automatically re-rates itself for ambient temperature variations and allows safe momentary overloads to pass without tripping the breaker. Yeah, so here we have it here. Here is our bimetal, here is our latching mechanism, here is our coil. So those two devices are operating on opposite sides of the latching mechanism, but either way, once they cause the latching mechanism to move, then our contacts will open. And here we have a little graph of the time current characteristic. So this one looks a bit odd, right? All the other ones we saw before have a nice even curve all the way down, but that's because if we think about it, we've actually got two separate and distinct protection devices. So it's almost like a combination of two different device curves, if you like. So in this first part here, this is the thermal action only. So that's wish this little thing would go away. Can I move it? No. Bugger. Okay, so we'll wait for that to go away by itself. There we go. And it has our current at the bottom, 20, 10, 20, 30, 50, 100, etc., etc. So around here we've got about 20 amps. This is our 20 amp line here. So somewhere around the 20 amp mark, it's going to trip, over 100 seconds. This is the number of seconds that it's going to trip in. So over 100 seconds. Once we hit the 20 amps, it's going to start coming down pretty quick. So we're going between 100 seconds for 20 amps down to a bit over 10 seconds for 30 amps. That's our thermal action only. So that's the heating time, the time it takes for that bimetal to heat and start to open. Once we start to get it up towards 50 amps, by the way, if we look here, if that line is 20 amps there, and we're talking about 100-second tripping time, so this must be maybe a 16 amp breaker or something like that. Anyway, once we start getting up towards around 50 amps, then we've got thermal and magnetic. So this line continuing here, if we think about that line continuing there, would be thermal only. And remember, our current characteristic, our time current characteristic graph tells us that, inverse time current characteristic, that as the current increases, then the time it takes to trip is going to go down. So it will continue to go down, but still not very fast. We want it to trip a bit faster than that. Once we're getting to this 50 amp range, then that thermal and magnetic action will happen simultaneously. And by the time we get to 500 amps here, then our tripping time is 0.01 seconds, so very, very fast. Over those sorts of loads, then we're talking about instantaneously tripping on the magnetic side. As soon as that current starts to flow, bang, it's going to trip. Three-phase MCBs. Each section of a three-phase MCB is constructed as same as a single-phase MCB, however they are mechanically linked to three poles to ensure that all three phases disconnect in the event of a fault, even if the fault is only on one of the phases. That's important, right? So if our MCB was constructed so that it would only trip if there was a high current on all three phases, then we could get a really big overload, get a short circuit on one of the phases, it doesn't trip the others. So actually, effectively, it's three separate breakers. Just think of it as three separate breakers, and then that handle there, or the what do you call that? Somebody's watching this video, send me a text and tell me what you call that. The little thingy there is constructed so it's joined together, so you can't switch one without the other. So if circuit breaker number one trips because it has an overload, then as it moves, it's going to pull these other two down with it and switches off. I have seen circuit breakers, three-phase breakers, where it's actually just three individual circuit breakers, and then you have a little piece that slides over the top of the three individual knobs, three individual mechanisms. It slides over the top and joins them together. So that would turn three separate breakers into one three-phase breaker, and that is exactly what we have here. That's what that is doing. It's just the fact that they are joined here that makes it a three-phase breaker. Otherwise, completely separate. Pretty neat, huh? Okay, so let's have a talk about three-phase motor protection. Motor protection is important. It's a topic all of its own, right? We've seen the fact that that because of the inrush current on a motor, we have to treat motor protection or circuit breakers, circuit protection, overcurrent, short circuit protection, all those things. We have to treat that a little bit differently for motors. So basic performance of protection are overload, so that's our high current, our phase failure, what we call single phasing. So if we've got a three-phase motor and we lose one of the phases, that motor still may operate on two phases, but it's going to draw a heck of a lot more current. Think about it as losing a cylinder on your car. If you are running on fewer than all of the cylinders, then your car is going to run very badly. It may do itself some internal damage, and you are going to need to push it significantly harder, as in drawing more current, to keep it operating, or to keep the car moving at the same speed. What else? Phase reversal. So in a three-phase motor, if I reverse the phase, let me go back. Phase failure, so we call it single phasing. Here's just a little tip here, because this is something I remember warping my brain somewhat, is if we lose one phase, so we still have two phases, but we've lost one, we call that single phasing. Now, I don't know why. To me, when you say single phasing, that would mean you've got one phase. Why don't we call it dual phasing? Well, we don't. We call it single phasing. It is what it is. I'm sorry about it. I hate that phrase because it sounds stupid, but there you go. Phase reversal, right, a three-phase motor. If we haven't talked about this before, then I can tell you now that if I have three phases, three lines, and they are connected to three terminals in a motor, and the motor turns, if I take any two of those phases and switch them over, could be these two, could be these two, could be these two. If I take any two of those three phases and switch them over, the motor will change direction. What? Neat, huh? So that's great. That's a really great tool that we can use. I can change the direction of any motor. I just change two of the wires. Cool. But we don't want that to happen accidentally. Sometimes. Well, it depends on the type of thing, right? So some motors need to be going up, forward and reverse. What's an example? A garage door opener is a great example. It's got to go up and it's got to go down. If I accidentally somehow reverse the phases on that, well, then when I push up, it's going to go down, and when I push down, it's going to go up, which is not ideal, but I'll be able to figure that out, right? I'm probably not going to cause myself too much hassle. I just go, I have to push the other button. That's weird. If you have a production line, let's say big motors that are dragging logs down a production line with in a milling operation, so the logs will then be like debarked and cut into slices and so on and so forth. Imagine the carnage that would happen if I reversed all the motors and something like that, and we had logs getting pushed back up the chute rather than coming down the way they're supposed to. We could be very, very dangerous. So in that case, those types of cases, we need to have some sort of protection against phase reversal. And we want low voltage or loss of supply protection as well. So this is where if the power gets turned off for whatever reason, then we need some sort of no volt supply, which means that when the power comes back on, it doesn't automatically restart. So if you think of, say, the lights in your house, right? So if the power goes off and you leave the light switch on, then when the power comes back on, the lights will go on. So they automatically come back on because the switch is left on. We don't want that to happen with most motors. Why? Because once the power goes off, everything stops. And again, so let's say we're talking about that imaginary milling operation where I have big logs getting dragged everywhere. If the power goes off, okay, well, we have to stop. The last thing I want is when that power goes back on for everything to restart by itself, because it's a very high likelihood that things are going to start getting flung all over the place, and that's not what we want. So we need some sort of no volt protection, which means that when the power comes back on, I still physically have to go and reset that machine, motor, whatever it is. I've got to turn it back on before it'll restart. Okay, overload protection for motors. To protect the motor against overload, overcurrent relays are used. The main type are magnetic and thermal. That rings a bell, huh? The magnetic relay shown in the figure below lifts a plunger and trips the starter contactor when a specified value of current passes through the solenoid coil. So this one's actually linked into our it's linked into our contactor, right? Our start to stop button with our contactor. We saw that in our circuit control unit. This is a overload that's linked into that. The magnetic relay needs to provide protection against a sustained overload, 1.25 times the full load current, but still allow a momentary overload to start up at 6 times full load current without tripping. So that's our start current, remember. To achieve this, there must be a delay in the tripping action. The delay device is an oil-filled dash pot. Don't ask me what a dash pot is, I don't know the answer. The thermal relay operates on the principle that a bimetal strip bends when heated. So on and so on. Do I need to talk about that again? It's a different context because this is happening inside a motor overload. So a motor overload is a device we'll install. You can usually on the contactor for that motor. Generally, a motor will be controlled by a contactor. The contactor is controlled by our push button stop start, and then each contactor will have its own little overload connected to it. But in this case, the thermal overload is going to operate in exactly the same way as we've talked about for our MCB, so I don't think I need to go into that again. You guys are welcome to read this bit yourself. Phase failure protection. A moment, let me just figure out where I'm at. Okay, let's finish motor protection, then I'll stop this one and go to the next video. Phase failure, also called single phasing, means the interruption of one of the supply lines to the motor. So, as I said before, single phasing means we've lost one phase. We still have two phases, but we call it single phasing because we've lost one phase. A three-phase motor will not start under these conditions because it effectively connected a 400 volt single phase supply between the two remaining supply lines. That may or may not make sense to you. Take that for what it is at the moment. We need all three phases for a motor to start. It'll run on two phases, but it won't start on two phases, and for the exact same reason that a single phase motor will run on single phase, but it will not start on single phase unless I add a capacitor in there to give me a bit of a little bit of phase displacement or put my two windings out of phase. There's a little head start for you, a little teaser for when we talk about single phase motors. Yeah. Anyway, however, if running, the motor will continue to run but at reduced speed with increased current on the two remaining supply lines, as I mentioned that earlier. For small motors, adequate protection is usually provided by an overload relay in each line to detect any increased current. For larger motors, or where for safety reasons positive detection of phase failure is required, protection devices incorporating a different tripping mechanism are used. Right, so that's telling us that as in the previous slide, I said there was most motors will have an overload on the contactor itself, and that overload in general, in most cases, will give us enough protection. So if we lose a phase, then we're going to get a high current in the other two phases. As I said, it will keep running on two phases, but they'll be at significantly higher current. That high current will then be, in most cases, enough to trip that overload. As it says there, for safety reasons or for other reasons, we need to have some sort of, it says there, positive detection, so some sort of specifically when that phase is dropped out, we need to know, rather than just relying on overcurrent. Then you'll have a different tripping mechanism, which we don't need to go into here. And what do we have there? The bimetal heaters for each phase are carrying the same current and therefore bending evenly in response to the load current. In this case, they provide normal overload protection. Here we have that here. Here are our bimetal strips. Right, and then as current is going through, then they're going to bend, but they'll be the same. The figure below shows the effect of a phase failure, where loss of current to heat the middle bimetal strip imparts an additional tripping movement to the toggle lever. This causes the trip contacts to open and the motor contactor to disconnect the motor supply. So that's worth noting there, right? So we can see the bend in this one here. That means as it heats up, it's bending this way. So the bottom of it here is moving to the left. And they're all moving in sync with each other, which is fine. If I lose one phase, not only will these two outer ones, so we've lost the middle phase in this example, not only will the two outer ones bend more to the left because they are getting a higher current, so they're going to bend more. The middle one now has no current, so it's going to start to bend back. So now they're working against each other, which will increase the likelihood of tripping. So that's how the bimetal or how the thermal overload is able to protect us or protect the motor in the case of a phase failure. Phase reversal. Alright, actually, let's stop there. We'll go on to the next video. So this is end of part 3. Your code, third digit of the access code is 8. Cool. See you in the next one.